Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about uncorrelation, which is the lack of linear dependence between two quantities, and we're going to compare it to independence, which is the complete lack of dependence between two quantities. Let's get started. We're going to talk about uncorrelation and independence, and our goal is to establish the difference between the concept of uncorrelation and the concept of independence. Let's remind ourselves what we mean by correlation. If we have two random variables A and B, where the correlation coefficient and the covariance are positive, if the correlation coefficient is positive, then the covariance is also positive. In this case, 0.75 for these samples here. Then we say that A and B are positively correlated, which means that when we try to estimate one of them using the other, using a linear estimate of the other, then the linear estimate is directly proportional. Okay, we have a line with a positive slope. In this case, the slope of the line is equal to the correlation coefficient because these two random variables have zero mean and unit variance. The residual is obtained by subtracting the linear estimate from the samples. What happens if the correlation coefficient is negative? Then we say that the two random variables are negatively correlated because, again, when we try to estimate one using a linear function of the other, the slope is negative, which indicates that they're on average inversely proportional. Again, here we're showing just the residual. When we say that two random variables are uncorrelated, what happens is that when we try to estimate one using the other, the estimate is flat, it's constant, we give up. There is no linear dependence between the two random variables. We cannot do better than just saying that the random variable that we want to estimate, in this case B, is just equal to a constant. In that case, the correlation coefficient and the covariance are zero. Okay, and as you can see, the residual is just equal to the original samples. Independence, which is complete lack of dependence between two random variables, actually implies uncorrelation, which makes a lot of sense because uncorrelation is lack of linear dependence, which is a form of dependence. If A and B are independent, then the covariance, which is equal to the mean of the product minus the product of the means, is actually equal to zero because under independence, the mean of the product is actually equal to the product of the means because essentially if the two random variables are continuous, then their joint PDF factorizes into the product of the marginal PDFs, and if they are discrete, the joint PMF factorizes into the product of the marginal PMFs. You can go back to the videos on averaging to see a proof of that, but it's really simple. So under independence, the mean of the product factorizes into the product of the mean, so these two terms cancel out, and the covariance is zero. The two random variables are uncorrelated, which again makes a lot of sense because correlation is a form of dependence. In general, we're going to see that independence implies uncorrelation, but uncorrelation does not necessarily imply independence. However, there is an important exception, which is Gaussian random variables. Let's take a look at two Gaussian random variables with zero mean and unit variance. The same results apply for general Gaussian random variables, but this is just to simplify the exposition. And we're going to say that the Gaussian random variables are uncorrelated. What does this mean in terms of the parameters of the Gaussian distribution? Where we saw in the previous video that the off-diagonal of the covariance matrix contains the correlation coefficient between the two Gaussian random variables. So if they are uncorrelated, that means that that off-diagonal is going to be equal to zero. So the distribution only depends on this covariance matrix parameter because we're assuming zero mean just to make our life easy. But it makes no difference. You could repeat the same argument for non-zero mean Gaussian random variables. The inverse of the covariance matrix parameter is really easy because it's the identity. The inverse of the identity is just equal to the identity. So now let's take a look at the joint PDF between the two uncorrelated Gaussian random variables. This is the formula, the general formula for the joint PDF of a Gaussian random vector that has zero mean, otherwise we would have to include the means there. Here we're going to plug in the identity, and the determinant of the identity is just equal to 1 because it's the product of the diagonal. So we get this expression where does this come from? Well, it comes from A transpose B times the identity times AB is just equal to A squared plus B squared. We see that the joint PDF actually factorizes into the product of these two terms, which happen to be the marginal PDFs because they're valid Gaussian PDFs that integrate to one and only depend on the respective variables and have zero mean and unit variance. So this proves that in the case of Gaussian random variables, if we have uncorrelation, that immediately implies that the joint PDF is going to factorize into the marginal PDFs, which implies complete independence between the two random variables. Let's take a look at what are the implications in terms of the actual joint PDF. So for that, we're going to take a look at some pictures. So this is how the contour lines of the joint PDF look like if there is negative correlation. This is how they look like if the correlation is zero, and this is how they look like if the correlation is positive. So in our case of interest, where the correlation is zero, we have those contour lines. Let's take a look at the implications in terms of the conditional distribution of one random variable given the other. Okay, so we have these contour lines. Now we're going to slice this and take a look at what is the distribution of B when A is fixed to be equal to -1, 0, or 2. We could have picked any values. A more fancy picture where we see the joint PDF actually coming up. We're basically slicing the joint PDF at different points where A equals -1, A equals 0, and A equals 2. So what happens when we take those slices and we renormalize them to obtain the conditional PDF? Remember that we always have to renormalize dividing by the marginal so that the conditional PDF actually integrates to 1. Well, what we're going to see is that they are exactly the same and exactly the same as the marginal PDF. So I know that you knew this from when we talked about independence of random variables, but I just wanted to really drive home the fact that for Gaussian random variables, if they are uncorrelated, that means that the conditional distributions are exactly the same. We have complete independence. And this is going to be in contrast to most other situations. This is why I wanted to emphasize this. Let's take a look at a really simple situation where we have two random variables A and B. B can have values -1, 0, and 1, and A can have values 0 and 1. Okay, and I have drawn here the joint PMF, which is very simple. There's a 0.5 probability that we're at 0, 0, 1/4 probability of being at 1, 1, 1/4 probability of being at 1 - 1. Let's compute the covariance between these two random variables. First of all, what is the mean of B? Well, to compute the mean of B, we just sum the possible values of B over all, weighting them by all the values of the joint PMF. So that would be 0 times 1/2. Here it's equal to -1, so -1 times 1/4. And here it's equal to 1, 1 times 1/4. And you see here that we get 1/4 minus 1/4 equal to 0. So B is 0 mean. Now let's compute the covariance between A and B. The covariance is the mean of the product minus the product of the means. Because this guy is 0, we can just compute the mean of the product. What are the possible values of the product? 0, 1, and -1. So it's very easy to compute this mean. Again, we sum all the possible values times the corresponding probabilities. 0 has probability 1/2, -1 has probability 1/4, 1 has probability 1/4. So the covariance is 0, which means that the two random variables are uncorrelated. Does this mean that they are independent? Absolutely not. And this is very easy to see when we consider the conditional PMF of B given A equals 0. We see that when A is equal to 0, there's only one possible value for B. So the conditional PMF is very simple. It's equal to basically the probability that B is equal to 0 is equal to 1. Okay, the conditional probability that B is equal to 0 when A is equal to 0 is just equal to 1 because that's the only value. All right. When A is equal to 1, B can have two values with the same probability, 1 or -1. Okay, so the conditional probabilities are one half assigned to 1, one half assigned to -1. Obviously, these two distributions are extremely different. So this means that clearly A and B are not independent, because when we change A, we completely change the distribution of B. However, they are uncorrelated. So this shows you that uncorrelation does not necessarily imply independence. An important case where we see this happen over and over when we're dealing especially with real data is linear regression. So remember that when we were talking about the decomposition of variance that occurs when we try to express random variable in terms of its linear estimate given another random variable and the residual, we explained that the residual was actually uncorrelated with, in this case, A. And this made a lot of sense, because if it had been correlated with A, we would have been able to improve the linear minimum MSE estimate of B given A, which is impossible because it's the best estimate. Okay, hopefully you remember that argument. But the point is that every time that we compute the best linear estimate of B given A, the residual is going to be uncorrelated with A. Okay? Does that mean that the residual is independent of A? We are going to see. So we're going to look at a real data set of NBA players that we have been working with, where we're trying to estimate rebounds, assists, points from height. Here in particular, we're going to look at rebounds and height. This is the ordinary least squares estimator. I haven't written minimum mean squared error estimator because we're computing it from data. Okay, but this is an approximation of the minimum mean squared error estimator. The residual looks like that. If I compute the sample correlation coefficient between the residual and height, I find that it's exactly 0. So height is uncorrelated with the residual as expected, because if it wasn't uncorrelated, we could improve this line and obtain a better estimate in terms of a least squares cost function. Okay? So the question arises, is this residual independent with height? Now let's think what that would mean. That would mean that, for example, if we pick a height here, this distribution of points, okay, should be the same as this distribution of points or any other. Obviously, that's not the case. In particular, here, we have much more variance than here. For some reason, we have much more variance in the error for tall players than for short players in the amount of rebounds that they get. Okay, so there's more variance in the rebounds that tall players get, which kind of makes sense, right? Because tall players get more rebounds in general, so there might be more variation, whereas it seems that small players, get short players catch less rebounds, and there's less variance there. Okay, so if we look at the conditional, just to make sure, let's take a look at these conditional distributions computed from the data. Okay, so actually I wanted to make that argument here. I got carried away. So again, we're going to slice this and this to look at the conditional PDF of the residual given different heights. If they were independent, those slices, once we renormalize them, should show the same distribution like in the case of the Gaussian. But we're going to see that they're very, very different because of this difference in the variances that I explained a moment ago. This is the distribution that we get. We're estimating the distribution like a histogram. When the height is equal to 185 centimeters, you see that there's not that much variance. And there's much more variance when the height is 211 centimeters. This indicates that there is nonlinear information about the rebounds that is not encoded in the linear estimate. In contrast, in the case of the Gaussian, all of the information is encoded in the linear estimate. All right, so what have we learned? We have learned that independence implies uncorrelation always. We have learned that uncorrelation does not imply independence. We saw a couple of examples of that. And we also saw that for Gaussian random variables, it does. For Gaussian random variables, uncorrelation does imply independence. And that's all I got. Thank you very much.